Welcome back to my course Aspects of Biochemical Engineering. In the last lecture, I tried to discuss the stoichiometry of bioprocess, and stoichiometry of bioprocess basically deals with the intermolecular relationship of different components present in the reaction mixture, and also we can determine what is the theoretical limitation of this particular process. And in addition to that, the stoichiometry gives two information. One is the validity of the experimental results, and another is the that amount of heat evolved in the biochemical process. As you know, that most of the biochemical processes are usually operated at ambient temperature and atmospheric pressure, and particularly since we are in the tropical country, our during summer the temperature rises to as high as 45 degrees centigrade. So, we since it is a exothermic reaction, so we required a lot of cooling requirement in the to maintain the temperature close to 35 degrees centigrade. So, that is why we want to we can calculate how much heat evolved through this biochemical process. Now, today I want to discuss the very important topic, that is reaction thermodynamics. And as you know, the thermodynamics is a very important topic, and it deals with if you look at it, deals with mostly the heat and temperature with the relation to energy and work. That now this thermodynamics that increases the efficiency of the steam engine, we call it Carnot cycle. We know this is the Carnot, this is the in the name of French physicist Nicolas Leonard Sadi Carnot in 1824, and he developed the thermodynamics, how to increase the efficiency of the steam engines. Now, but chemical, we are interested here mostly on chemical thermodynamics. Chemical thermodynamics studies the nature of the role of entropy in the process of the chemical reaction, has provided the bulk expansion and knowledge of the field. So, we basically discuss that how entropy the affects in the chemical reaction, and also we will discuss some kind of Gibbs free energy changes that affect the chemical reaction. So, in this lecture I divided into two parts, the chemical thermodynamics 1 and chemical thermodynamics 2. Chemical thermodynamics 1 mostly deal with the thermodynamics as a whole, how it looks, and chemical engineering thermodynamics 2 mostly I shall discuss on the thermodynamics of the chemical process. Now, if you look at first, let us try to find out what do you mean by system and surroundings. Now, system, if you look at here, that system is a part of the physical universe under study, and while the rest of the universe is the surrounding. Now, suppose a beaker, this is the let us assume a beaker, and inside the beaker we have water, and this is we consider a system. Now, system lying on a table, and this is all the other than the beaker, whatever we have, that is we call it surroundings. So, there should be this is how system and surroundings can be defined. Now, if you look at again system and surroundings, we have three different systems, like we have isolated system, open system, and the closed system. Now, let us see what do you mean by isolated system. Isolated system means that no transfer of mass or energy across the boundary of the system. So, here this is the system, and there is no energy and mass transfer take place, and since there is no energy and mass transfer take place across this boundary, we call it isolated system, and it is perfectly insulated and impermeable. A gas confined in a piston cylinder arranged in the wall of which are made of insulated material. So, this is Now, next is the open system. Open system, what is happening, both the mass and energy can transfer. You see here the mass transfer, it is the energy transfer that that transfer take place between the the system and the surroundings. Now, we call it the open vessel having a liquid. That is, we can give the example of the system. Now, closed system, what is happening in the closed system, the energy can transfer across the boundary, but not the mass. So, here the energy transfer take place, but not mass. A gas confined in a piston cylinder having good thermal conductor. So, the energy transfer take place, but due to good conductivity of the material, some kind of energy transmission take place, but not mass. If it is this, we call it closed system. Now, another very important term is there, what we call thermodynamic stress. Now, what do you mean by thermodynamic stress? We have two different property. We have, one is called point property, another is path property. Point property means one point, initial point and final point. Now, initial, that change of property value depends on the initial and final stage. So, suppose temperature is the entropy, the initial entropy was S1 and final entropy S2. So, change of entropy is S2 minus S1. This is, we call it del S. This is the entropy change, enthalpy change and internal energy change are there is a point property. And what is the path property? Change of property value depends on the path by which the process carried out in addition to initial and final. How these changes take place, as for example, work and heat transfer, how they take place in between the system. If you look at the Carnot cycle, we have, this has been done very nicely, that how this path property can be done. Now, another, if you look at the properties of the system, that we have two properties. One is called extensive property, another is intensive property. Now, extensive property deals with the quantity of matter specified in the system. Now, as for example, when we call it mass of the system, mass of the material, volume of the material, then it is kind of extensive property. Intensive property independent of the system size. As for example, pressure, temperature, specific volume. So, we have two properties as per thermodynamic system is concerned. One is called extensive property, another is intensive property. Now, if you come to the process, we have two type of process. One is called isothermal process and adiabatic process. Now, isothermal process, basically the temperature of the system remains constant, and adiabatic process, the heat transfer remaining constant. There is no heat transfer take place. That is how this is defined. Now, in case of isothermal process, it attains that the temperature is constant either by removing heat or supplying the heat to the system, as for example, melting of ice. Now, another, we have the reversible process. And the reversible process are those processes in which the changes are carried out slowly, that the system and surrounding always are in equilibrium. This is called reversible process. Now, I can give a very typical example. Suppose there is a system comprises of A and B and they are in equilibrium. Now, if you increase the temperature of A, then what will happen, that heat will transfer from A to B, the kind of. Now, if you cool the temperature of A, then heat will flow from B to A. So, this is what is metal, that two metals jar AB, which are in thermal equilibrium, are in contact with each other. Now, when the heat jar is slightly, heat starts flow from jar A to jar B, and this is the direction of the of this process. Now, this process can be reversed just the cooling the jar slightly. Then when the jar is cooled, heat flow from B to A till the thermal equilibrium reach. Now, another process we have that is called irreversible process. Now, if you look at irreversible process, that we have this process cannot be undone by exactly reversing the changes of the system. All spontaneous processes are irreversible, all real processes are irreversible. That is, irreversible means we want to mean the unidirectional, and reversible means the bidirectional. So, so this process cannot be undone by exactly reversing the change of the system. That is why we call it irreversible system. Now, let me discuss about the first law of thermodynamics. What is the first law of thermodynamics? It states that energy can neither be created nor destroyed. The total energy of the universe or isolated system is constant. So, this is the first law of thermodynamics. Now, another form we can explain like this: the change of internal energy of a thermodynamic system is equal to the heat energy added to the or lost by the system plus work done on or by the system. This can be mathematically, or this is expressed like this: del U equal to Q plus W, where Q is we considered as the heat energy that change that take place, and W is the work, and del U is considered as the change of internal energy. Now, Q assigned to be positive, Q assigned to be positive value when heat is absorbed, but it is negative when heat is lost by the system. So, one is the endothermic, another is exothermic. So, W is assigned positive when its work is done on, but negative when work is done by the system. Now, for processes that do not involve the phase changes, the positive value of internal energy results in temperature increase. So, if we do not have any change of phases, then change of internal energy positive, that indicate temperature will rise in the process. Now, enthalpy, there is another very important term, what we call enthalpy. That enthalpy is the measurement of energy in a thermodynamic system. Now, how we can define this is equal to internal energy plus P into V. V is the work done by the system. This is internal energy plus P into V. Now, if at constant pressure, then P into del V is the kind of work done, and this is the internal energy. The change of internal energy is the H product minus the H reactant. Now, we have two type of reactions, as you know. One is called endothermic reaction, another is the exothermic reaction. Endothermic reaction means we mean that absorb the heat from the surroundings, and in endothermic reaction feel cold, where del G is always greater than 0. I can give the example when glucose, when we make a solution in the water, then the temperature cools down. That is the kind of example of the endothermic reactions. The exothermic reaction is the transfer of heat to the surroundings. I can give the very simple example: heating of wood or heating of coal, where the temperature increases. The exothermic reaction feel hot, where del G is greater than less than 0. That del G always should be negative, and here del H is negative, and here del H will be positive. Now, let me come to the entropy, because which is very important property of thermodynamics, and it is a measure of randomness or disorder of the chemical system. If we have high entropy, the question comes how you define entropy. entropy is the S is the, this is equal to dq by T. dq is the heat change that take place, and T is the temperature that we have. So, now the high entropy change is the highly disordered system, and low entropy change, that means well organized system. No such thing as negative entropy. Now, del S of a chemical reaction we can always express as entropy of the product minus entropy of the reactant. As I explained that at a constant temperature, the entropy change of entropy can be explained like this. This is how we can explain, where Q REV is the heat that is transferred when the process is carried out reversibly at a constant temperature, and T is the temperature in Kelvin. So, capital T always we indicate as a Kelvin. Now, if you look at the reversible system, ideally that ideal reversible system, that change of entropy of the universe, that is equal to that the change of entropy of the system plus change of entropy in the surrounding, that should be equal to 0. Now, in case of irreversible process, what we call real and spontaneous, the change of entropy in the universe equal to change of entropy of the system plus surrounding, that should be always greater than 0. That is in case of spontaneous system, always the entropy will be higher value that we have. Now, exothermic reaction and positive entropy, as I told you, this is called spontaneous, and in case of endothermic reaction and negative del S, we call non-spontaneous. So, this is the two type of reaction that we have, and on the basis of change of entropy, we can easily find out what is the nature of the reaction, whether it is spontaneous or whether it is non-spontaneous. Now, this is very interesting that if we how we can monitor the exothermic reaction, how system and surrounding influence the entropy change of the system. Now, here all are the examples of the exothermic reaction, and under what circumstances we have the exothermic reaction. Now, let us take the first instance for a exothermic reaction in which change of entropy of the system, this is the change of entropy of the system is positive, and change of entropy of the surroundings is positive, then in change of entropy of the universe should be positive. The reaction will be always spontaneous. Now, in case of the change of that entropy is negative, but if the change of entropy of the surroundings is more than change of entropy of the system, then this entropy of the universe will be positive. The another instance we have for a endothermic reaction in which the change of system is positive and change of entropy in the system is positive, but change of surroundings also smaller than that of the change of entropy of the system, then surroundings will be also positive. And this is also example of the endothermic reaction. So, in second law of thermodynamics is that the universe spontaneously tends towards the increasing the disorder or randomness. This is the nature of the system that we have. It always tends to increasing the disorder or randomness, and mathematically the change of entropy of the universal, that will be always greater than 0. Driving force of the spontaneous process is an increase in the entropy of the universe. As I told you, this is the real system that we have, that always the entropy should be positive. Another very interesting term that we have as far thermodynamics is concerned, what you call Gibbs free energy change. Now, Gibbs free energy change is the thermodynamics potential that can be used to calculate the maximum reversible work at constant temperature and pressure. that is isothermal or isobaric. Isothermal means where temperature is remaining constant, isobaric means where the pressure remaining constant. Now, absolute value of G or free energy, the free energy cannot be measured, but change of free energy can be measured. So, mathematically it can be expressed like this: change of free energy equal to del H minus T into del S, T is the Kelvin, measured in Kelvin, and as standard condition, standard free energy change equal to standard change of enthalpy plus T into standard change of that entropy of the system. So, this is the equation we should remember for calculating the free energy change. Now, if you look at the del G, if del G is negative, free energy change is negative, the forward reaction is spontaneous, and if del G is 0, then this is in equilibrium, and del G is positive, the reaction is spontaneous in the reverse direction. Reverse direction means I want to mean there is A to B, this is the reaction that we have. If this direction is there, then del G should be positive, then del G will be positive. But if we have this A to in the reverse direction, then del G, sorry, this is negative. This is in if del G is negative, then it is spontaneous A to B. But if del G is positive, this is positive, then if it is reverse direction it will be spontaneous, but this direction it is not spontaneous. But at the equilibrium condition, that equilibrium condition, what will happen, del G, the change of internal energy, that should be equal to 0. Now, this is the reaction spontaneity and the sign of del H, del S and del G. So, this is if here if del H is negative, and now if you look at previous, so we have this equation that we shall have to remember this equation, del H equal to del H minus T del S. Now, if you see it, so you have, I can write like this, del G equal to, we can del G equal to del H minus T into del S, am I right? Now, we can compare here. If del H is positive and del S is positive, then this is negative, and del S is negative, and then del H is negative. And if this is negative and this is negative, then this will be negative. So, this will be spontaneous at all temperature. Now, if del H is positive and del S is negative, then this will be T into del S will be positive, then del H will be positive, then it is non-spontaneous at all temperature. Now, here if del H is positive, del S is positive, del H is positive, and del S is positive means this is negative, and this may be plus or minus. So, it may be at spontaneous at high temperature, non-spontaneous low temperature. Now, if del H is negative and del S is negative, then this will be positive. Now, again the change of free energy, it may be plus or minus. The spontaneous has lower temperature. This is the reversible of this. If you whatever we have and whatever we have, just reversible of this, and non-spontaneous at high temperature. Now, this is the problem that we also try to work out, that how this we can use for calculating the temperature required for any kind of reaction, chemical reaction. Now, let us assume that del H of the reaction is 158 kilojoule and del S is 411 joule per Kelvin. Now, this is the equation we have, and so in case of spontaneous reaction, that del G should be less than this value, this is equal to del G, this value should be less than 0. That means it should be negative. Then and only then it should be spontaneous. Now what we can write? We can put these values here. We can put the value here, that that value of H and value of S we can put, and then we can interchange. We can find T is greater than 384 Kelvin. That means if we wanted to have the spontaneity of the reaction, we shall have to maintain the temperature at 384 degrees centigrade. So this is a very interesting problem, how we can determine the that is spontaneous of the reaction at a different temperature. But this is the, suppose we want to, because whenever we carry out any kind of chemical reaction, we are interested to make it spontaneous to get more product. So naturally that so question comes that under what circumstances it can give the more product. So this is one very interesting thing that we have. Next problem that I have, that is calculate the change of entropy by heating 100 grams or 100 kg of water from 27 degrees centigrade to steam at 100 degrees centigrade. Specific heat of water is this much, and latent rate of vaporization of this also we can calculate very easily. As you know, the change of entropy for heating 100 kg of water from 27 degree to 100 degrees centigrade, we can calculate at m Cp into dlnT. So I have already told you that del S equal to what? Del S equal to dq by T. Am I right? So when you heat water, what is happening? What is the ms into del T? The del T by del T. So this is equal to ms. This is dln T that we have. So we can have similar type of expression here. So mass is 100 kg, that is given there. This is the specific heat of water, and this is the ln. This is the temperature. This is 100 degrees centigrade, and this is the 27 degrees centigrade. So this is the change of enthalpy that we have if we heat the water from 27 to 100 degrees centigrade. Now if you do the vaporization, the equation will be different. The reason is that vaporization takes place at 100 degrees centigrade. It is kind of phase change from the liquid to vapor, and latent rate of vaporization is this 23 into 10 to the power 5 joules per kg. Then we can 100 into, if we calculate that, we can find it very easily, that the 100 into this equal to heat, and this is the temperature that we required. So this is how we can calculate the change of entropy for the evaporation. So so we can calculate this entropy of the system very easily. So what we learn in this, that we want to find out that what we mean by thermodynamics. Thermodynamics basically it is deals with the temperature, and it basically it deals with the mass and temperature, also how it relates with the energy, and then we try to find out define the system and surroundings, how this affects the system, and how we can define the spontaneous system and non-spontaneous system. And spontaneous system and non-spontaneous system can be explained with respect to entropy, with respect to free energy change. Now when you talk about the entropy, in case of spontaneous system, the entropy keep on increasing, but in case of reversible system, the change of entropy should be equal to 0. Now in case of free energy change, we find out that in case of exothermic reaction or spontaneous reaction, change of entropy should be negative, and in case of non-spontaneous reaction it will be positive. But if you do the reverse reaction, then it should be, we can convert it to the spontaneous. But I hope in the next lecture this will be more clear when we deal with other different type of reaction. Thank you.